Hello, welcome to this learning module. In this video, we're going to orient ourselves to the NMR spectrum, understand what we're looking at, what the pieces are, and how to read it. We're not going to learn how to solve the NMR spectrum in this video. We'll do that a little bit later, but right now we're just going to learn about what we're looking at. What is represented in the NMR, and what information do we get out of it? It's a little bit more complicated than mass spec and IR, so we're going to spend a little bit more time talking about what we're looking at. So the first thing to point out in an NMR is there are several signals in an NMR. An NMR will always contain one or more signals. And each signal may contain one or more peaks within the signal. So when I look at this NMR has 4 signals. And each of those signals has a certain number of peaks within the signal. This NMR has 3 peaks within the signal, or this signal has 3 peaks within the signal. This signal has 1 peak within the signal. This one, 1, 2, 3, 4, 5, has 6 peaks within the signal. And this one has 3 peaks within the signal. So that's the first thing to say. Every NMR is split up into 1 or more signals. Each signal will have 1 or more peaks within the signal. What does that mean? We'll talk about that here in a second, but that's just the first thing to say. The x-axis for an NMR is another odd unit. With IR, if you remember, we had wave numbers, which was a proxy for energy. It was inverse reciprocal centimeters. We didn't really worry about it very much. It's going to kind of be the same thing here. Our units for the x-axis for NMR are given by this lowercase letter delta, and they represent ppm, parts per million. What does that mean? So the amount of energy that a nucleus needs to flip the spin is dependent on 2 things. We previously talked about how it's dependent on the amount of electron density around the nucleus, the amount of shielding, but it's also dependent on the magnet strength that you're using. So there are NMRs come in different magnet strengths, and they're usually measured in hundreds of megahertz. So the instrument that we have at Xavier University is a 300 megahertz instrument. That's pretty common. That's a standard workhorse NMR, magnet strength, 300 megahertz NMR, and that refers to how strong the magnet is. But 400 megahertz is also pretty common. 500, 600 is a little more powerful, a little more expensive, and so you can have all sorts of ranges of magnet strengths. But on every magnet, the amount of energy needed to flip the spin is slightly different. And that seems like a problem, because that would mean that the x-axis would be different for every NMR. You would have to know what kind of instrument you were using in order to read the x-axis. So we decided to cancel out, to correct for the magnet strength. So with the amount of energy needed to flip the spin, we divide by the magnet strength, and that gives us a standard x-axis, so that every hydrogen, or excuse me, a hydrogen will have the same x-axis value on every NMR. For any given molecule, every hydrogen will have the same x-axis value no matter what NMR you acquire the spectrum on, no matter what the magnet strength is. So this signal at 4, around 4 in this particular NMR, will show up around 4 on a 300 megahertz instrument, and a 400 megahertz instrument, and a 500 megahertz instrument. Doesn't really matter. And because magnet strength is measured in megahertz, millions of hertz, 10 to the 6th hertz, when we divide by the magnet strength, millions of hertz, that's where we get the parts per million unit for the x-axis. All that to say, don't really worry about it. What's more important is what number we're looking at, rather than exactly what the unit means. When we look at the x-axis, we can say a couple of things about the position of the signals on the x-axis. Signals that are closer to 0, these are the ones that are more shielded. These are the ones that have more electron density around the nucleus. And the term we use for these types of signals that are more shielded, that have more electron density, we call this region of the NMR the upfield region. Conversely, the signals that are down closer to 10 on the x-axis are less shielded. They have less electron density around them, and we call this downfield. And that's more of a relative term when you're comparing 2 peaks. So if I label these peaks A through D, which is probably a good idea, we'll call this one A, this one B, this one C, and the last one D. Then I can say that signal C is downfield relative to signal D. signal C is upfield relative to signal A. So that means that signal C, the hydrogens represented by signal C, somehow have less electron density. They're less shielded than the hydrogens around signal D. But the hydrogens for signal C have more electron density. They're more shielded than the hydrogens represented by signal A. So those are just some of the terms that we use. We'll use them so often they should start to become second nature over time. This NMR spectrum that we're looking at right now is computer generated, but we can also have real world spectra. This is a real world NMR spectrum, but the same things apply. It's still 0 to 10. In fact, these are NMR of the same molecules. So if you look at these signals here, they're the same signals that we see here with the same number of peaks within the signal. What I want to point out with this is a couple of things. First, this NMR is actually broken into two parts. The top part, the bottom part, is the hydrogen NMR that we're spending most of our time talking about right now. And this top part, overlaid on it, is the carbon-13 NMR. We haven't talked about carbon-13 NMR yet, but there it is. The x-axis for the proton NMR is here on the bottom, and in this particular view, the x-axis for the carbon NMR is here on the top. And notice the x-axis is different. It goes from 0 to about 240 parts per million. We'll talk more about that when we get to carbon NMR. The reason I bring this up is to talk about what it means to be a real-world spectrum. NMR is a solution-based technique. And what that means is, in order to acquire an NMR spectrum, you have to dissolve your sample in some kind of solvent. That's different than mass spec and different than IR. In mass spec and IR, you don't necessarily need a solvent. Sometimes you do anyway, but you don't necessarily need a solvent to do NMR, to do mass spec or IR. But with NMR, you need to dissolve your sample in a solvent. And that could be a problem because if we're looking at the proton NMR, the solvent that we use often has protons of its own. The most common solvent to use, because it dissolves lots of organic things, is chloroform, CHCl3. That's the most common NMR solvent. And if we dissolved a sample in chloroform and stuck it in an NMR, the amount of chloroform would be so much more than the amount of signal. There'd be so much more chloroform, billions of times more chloroform in the sample than there would be sample. And so that what would happen is we'd just see one huge peak for chloroform, and these signal peaks of interest would be really, really small if we could see them at all. And that would be a problem. So what do? We do a chemical reaction to turn chloroform into deuterated chloroform. We do a chemical reaction where we replace the hydrogen with deuterium. Now, deuterium is itself NMR active, but it is NMR active in a completely different region of the radio wave frequency. So when you go to the instrument, you tell it what nucleus you want to look at, and it only uses those radio wave frequencies to excite the molecule. So because deuterium is active in a completely different region of the radio wave frequency, we can cause chloroform to be essentially invisible in a proton NMR. By deuterating it, making it deuterated chloroform, it's effectively invisible in the proton NMR. Now, the chemical reaction that we use to turn chloroform into deuterated chloroform is not 100% perfect. Not 100% of the hydrogen atoms get converted into a deuterium atom. And so when that happens, we always end up with a slight amount of residual proteochloroform, a slight amount of chloroform that still has its proton. Chloroform, the hydrogen in chloroform would have a chemical shift of 7.2 ppm, roughly. We haven't really talked about chemical shift much yet, so don't get too concerned about that. Just accept for now that chloroform, the hydrogen in chloroform, would have a chemical shift of around 7.2. So if you look at this real-world NMR, you can see right here a very tiny peak around 7.2. That is the residual hydrogen from proteochloroform. So it will show up in essentially all of our NMR spectrum. Now, since we have the carbon overlaid on top of this one, I'll just go ahead and tell you now that the carbon signal in chloroform shows up here at around 77 parts per million. And in proton NMR, it showed up at about 7.2 parts per million. These are the signals from the solvent, the proton from the proteochloroform and the carbon from chloroform. And what that means is this is just the solvent that we dissolved the sample in, and so we can safely ignore the signals from the solvent anytime we see them in our NMR. This will really only more be a concern in lab. In lecture, we'll mostly get spectra that don't have these here, just because it complicates things. But you should be aware that that's what those peaks are. 7.2 is residual chloroform, and 77 in the proton NMR. The other thing that we do in NMR is we add an additive to the solvent in order to calibrate the x-axis. And the additive that we add is tetramethylsilane, silicon with 4 methyl groups around it. Tetramethylsilane. By definition, we have said that the protons in tetramethylsilane have a chemical shift of 0 ppm. So when you look at an NMR, you should be able to see a signal at around 0. This one's a little bit hard to see, but if I zoom in, you can kind of tell that that's a more bolded peak for around 0. And so the peak at 0 is the tetramethylsilane additive in the solvent that we use to calibrate the x-axis, which means it's also not part of our structure and can be safely ignored. So we can always ignore the solvent signal in the NMR and the tetramethylsilane, the TMS signal in the NMR.